Row or column counting is the idea of counting up multiple rows at a time and then using that information to do something with it. Looking at this red 3, you might be thinking, there is nothing you can do with this. There is no information to be gained here. Like with everything in Urjo, there are multiple options to figure out how to get information from this 3, but one of the most efficient things to do in this situation is to count the first and second columns. We don't know where they are, but we know that there are 3 more reds in the 2 columns. In 2 columns, the total number of reds you can have is 4. That's because each column has to have 2 reds. While these reds can be placed anywhere, something that is always true is that there's 4 of them in this area. That means for both of the columns, there are 2 reds. And that finally means that down here, there have to be both blues. This puzzle is not actually solvable, but it's an easy way to show a very useful way to use column counting. Anyway, that being said, column counting doesn't necessarily have to use this amount of rows or columns. It can use 3, it can, well, I guess it could use 4. I've never seen a case where it uses 4, but the logic is still the same and it still applies to any size of puzzle and any number of rows or columns. Now I'll do a bit more of a complicated example, and I'll do it on a 6x6 so that it kind of shows how you would use it on that sort of a situation. Well, now welcome to this situation. This is definitely a lot more of an intimidating one, but it's still solvable using counting. Let me show you. Okay, to start off with, let's calculate the number of blues around this 3, which is 4. Next, let's look down here, and down here we have another 4 blues. This next one's a bit tricky, but we know that there's 1 blue in this area of 2, which means we have 5 actually in this area. And then we can add up the 2 areas, the 4 and the 5, and then we can see that we have 9 total. So now, in this triple column, we know where all 9 of the blues' general area is. So everything outside of that we can put a red into. I'll put 2 of the reds into here, but there's actually another place the red goes. See if you can get where the other red can go to test your understanding. There's another rule which we call the quadrant rule, which comes as a direct consequence of this rule, and I'll show you how to prove that and then also how to use it. Okay, so here we have this corner here, and let's put it in a red box. We know that there are 5 reds and we know that there are 4 blues in this box. Due to the counting rules and them needing to add up to 9, we know quite a lot about these 2 boxes on the outside, and I'm going to color them blue because we know they're going to be the same amounts of red and blues, and we know both of them are going to have 5 blues and 4 reds. The rule that we call the quadrant rule is that the opposite cornered quadrants, aka the boxes, always have the same number of reds and the same number of blues. This actually comes in handy in quite a few different puzzles, and it allows some faster solves in using the methods. This is just an example and not a general proof, but it's pretty easy to see that if whatever you put in as those numbers, it will still hold true for. Okay, now here's a real-world example of how you would use this quadrant rule to speed up a solve by quite a lot and make it a lot easier. So the quadrant I'm using is going to be the bottom right, and then that also affects the top left, which gives a lot of information. So there has to be 1 blue up here, and a 4 must always be touching 4 of the same color. That means 2 of the reds have to be touching this 4, and that gives a lot of information because that's all of the reds in the square, so the rest of them have to be blue. Obviously I haven't solved the puzzle here, but this is the main way that the quadrant is used in this to get an advantage, and solving the rest won't really show anything new. So there we go, that's counting and the quadrant rule for you. Goodbye!